Hello and welcome to this video on the group 7 elements and displacement reactions from C4, the periodic table. My name is Mr. Clee. Hello and welcome. This video is on the group 7 elements and displacement reactions from C4, the periodic table. My name is... Firstly, the aims of this video. Essentially what you need to be able to do is to recall the appearance and uses of chlorine, bromine and iodine. You then need to recall the relative reactivity. Use that reactivity to describe and predict displacement reactions involving group 7 elements, and also to try and explain that reactivity using similarities and differences in the electron structure of the elements. So here's group 7 on the right hand side of the periodic table between group 6 and group 0, all in group 7 because they all have 7 electrons in their outer shell. Chlorine, the most reactive one that we can use. This is typically found in swimming pools and things like that, but it's also used in bleach production and was interestingly used in the First World War as chemical warfare. Here's an example of someone using an iodine-based antiseptic. It's also a disinfectant, just like chlorine, but it's not as damaging, it's not as toxic. I mean, you wouldn't scrub up using chlorine because you cause yourself a hell of a lot of damage, but you can do with iodine. So here is chlorine. Chlorine's a gas. It is also a green gas. Those are the two main things you need to remember. As well as the swimming pool thing, it's also used in sterilisation of tap water because it kills bacteria. It's also used in the production of pesticides, plastics and things like that. Bromine, although at first it might look like bromine is a gas, it's just a very volatile liquid. The liquid here is down the bottom of the flask. However, the flask itself is also filled with a dense orange liquid. It's used in water purification as well, and one of the main things that I'd say is pesticides. That keeps the trend of used to kill things, like you get with chlorine, bromine and iodine. And here is iodine. This is a grey solid. It does vaporise really easily and turn into a gas. It gives off a purple vapour, and it's used as an antiseptic on cuts and wounds, and also pre-surgery. If you've ever seen people being swabbed pre-having any sort of surgery done with a kind of browny liquid, that's an iodine compound. This graph sums up those patterns. What we have here is essentially an increase in boiling point and melting point as you go down the periodic table. So you go from gases at the top of the periodic table to solids at the bottom of the periodic table. This also includes fluorine and astatine, which we've not actually looked at. One other thing about the group 7 elements, when they react and form ions, we change the name. The -ene bit at the end, so it might be chlorine, iodine or bromine, changes to "-ide". So you get chloride instead of chlorine. So in this reaction here, this is potassium reacting with chlorine. In fact, probably isn't. It looks like it's sodium reacting with chlorine. So we'll be forming sodium chloride rather than sodium chlorine. When predicting reactions between group 7 and group 1 elements, this is the general equation. Using M to represent the metal and X to represent the halogen, you have 2M, or in this case, this example here, 2 lithium, reacting with X2, so in this case I2, to form 2MX, or in this case 2 LiI, confusingly. Good example of that. So another one would be sodium reacting with fluorine. 2 sodiums react with F2 to form 2 NaF. So this shows the reactivity. In my mind, this arrow is back to front. The arrow should go up. The most reactive of the group 7 elements is at the top. So fluorine is more reactive than chlorine, which is more reactive than bromine, which is more reactive than iodine, which is more reactive than astatine. Because of this pattern in reactivity, if you try to carry out a displacement reaction, i.e. if you get a group 7 element and try and react it with a metal halide of another group 7 element that is less reactive, so for example if you had chlorine and tried to react it with potassium bromide, then because the chlorine is more reactive than the bromine, the chlorine displaces the bromine from the solution. What you can see here in this picture is that chlorine is being reacted with potassium bromide. That's pushing the bromine gas out of the solution. Whenever you react chlorine with any metal bromide or metal iodide, that reaction will always take place. Same will happen if you try and react a bromine with a metal iodide. But this won't work the other way around, because the one that's free has to be more reactive than the one that's in compound. So you would not get a reaction if you tried to react bromine gas with sodium chloride. Here's an example of that equation again. This is clear potassium iodide, and chlorine gas being bubbled through it. You can see the colour change there. That is the colour of the iodine being pushed out of solution. This reaction here, Cl2 plus 2Ki, and the chlorine and the iodine effectively swap places, leaving the iodine on its own, I2, and putting the chlorine into the compound, so we now have potassium chloride. Finally, the reason for this. Similarities can be explained because they've all got 7 electrons in their outer shell, so they're all trying to gain 1 electron. However, the differences come from how easy it is these atoms, these elements, find it to gain that electron. The more reactive element, because it's trying to gain an electron, is fluorine, and that's because fluorine only has 2 electron shells, so its one space in its outer shell is closer to the nucleus. That means the attraction between the positive nucleus and the negative electron is stronger because they're closer. If that negative is further away, like in chlorine or bromine or iodine, then that attractive force gets weaker, which makes the element less reactive. So in summary, chlorine is a green gas, bromine an orange liquid, and iodine a grey solid. The more reactive halogens are at the top of the group. Displacement reactions only occur when a more reactive halogen is used with a less reactive one in compound, and we can explain reactivity through the presence of through the similar property that they're all trying to attract an electron into their outer shell, and it's easier to do so when the space that the electron is being attracted into, if you like, is closer to the nucleus. Thank you very much for watching. If you have any questions about this or any of the other videos in the series, please see me or any of your science teachers. Thank you very much. Goodbye.